All right, recorder re-rolling. Back up to the posters. So what we got so far? So we've covered all the preliminary groundwork, things like measurement, SI units, scientific notation, scientific method, vector components. We did all that. We did kinematic motion, that was linear motion, projectiles. We did dynamics, forces, Newton's laws of motion, had some atwoods, some inclines. Right. Now we're getting to, well, by AP's book, this is unit 3, and it's kind of a hodgepodge of different ideas. We got some centripetal force and rotational type motion going on. We're going to combine that with universal gravitation and make orbits is the big picture. Now, the way I taught this class too is I threw in some rotational kinematic stuff up here, right? Think about like turntables. So now we're not interested in how far, say, a car's gone in meters or miles, but how far is a turntable turn? You can measure that in degrees or revolutions, but we're going to tend to stick to radians for this section, right? All right, so we got angular velocity, how fast something rotating, angular acceleration, how fast something like speeding up or slowing down, rotating, right? Centripetal acceleration, centripetal force, right? So this is the force and acceleration associated with changing direction, right? If you're on a curved path, right? How much force, how much acceleration, right? Now the bottom 4 lines are actually more recent physics, but let's look at them real fast. Moment of inertia, there's your inertia in a rotational sense, resistance to change in motion, rotating. Torque, there's your R cross F. Angular momentum, I remember it's conserved. Remember like a figure skater question with that. Angular impulse is a transfer of angular momentum. Right, so that, all right. Here, this slide's pretty similar, but we're looking at rotational analogs. So in linear motion, time, rotational motion, still time in seconds. Let's say, right? Instead of saying how far in meters, now we're interested in how far have you turned in radians, right? Saying how fast meter per second, now how fast something rotating, radians per second. For example, the Earth turns, well, 1 rotation every 24 hours. That's a version of this. Right? Instead of a car speeding up or slowing down, now we've got a turntable speeding up or slowing down, rotating, right? Right, and then this bottom 4 lines is like, well, I guess more recent physics, right? Get a good look at that if you like, right? All right, let's look at a turntable, talking about some rotational kinematics. But you can link it back to linear motion, and the links are shown right here. So suppose we got 3 kids on a merry-go-round. You guys see we're up in a helicopter, right? You guys, everybody taking notes? Everybody taking notes? We're up here in a helicopter, looking straight down on these 3 kids on a merry-go-round. Give them a spin. And what does their motion look like? Well, they all have the exact same rotational motion. They have the same angular displacement, theta. They have the same angular velocity if it's rotating, and if it's same angular acceleration for that matter, if that matters, right? If it's speeding up or slowing down, spinning, right? But what if I want to know something different? What if I want to know like distance moved? Now, guys, the kid in the middle, doesn't he always have 0 distance moved? And it doesn't matter how far it's rotated, it's always 0 distance, right? But look, the further out you are, the further distance you go. You guys see that too? All right. So, okay, so now you can relate. Guys, look up here, reference to here. All right. All right. How far you moved around is angular displacement times your distance from the center, right? Now, the key, though, to make this work is that, guys, theta has to be measured in what unit for this to work? Radians, right? There's at least 3 different ways to measure angle, right? Degrees, revolutions, and radians, right? But anytime you directly multiply an angle in an equation, it has to be in radians, right? Now, if it's inside a sine or a cosine, just make sure your calculator is programmed for, and then maybe degrees are okay. But something like this has to be radians. Right? In fact, you guys know a specific version of this top formula. You guys have known since elementary school. Guys, 1 full trip around the circle is called 1 what? Circumference. Yeah, circumference could be the distance around the circle. Guys, what is circumference in terms of the radius of a circle? Circumference equals 2 pi r. That actually is a specific version of this, because 2 pi radians is 1 revolution. Oh, look at that. Circumference equals 2 pi r. Like we're guys, everybody look up here. Everybody look up here. Taking notes. Everybody's taking notes. All right. Same thing with the speed. Suppose you got over here on this grassy knoll, some guy has a radar gun, points it exactly at this kid in the middle. What does that radar gun read every time? 0. 0 mile an hour, 0 meter per second. Even if this thing's rotating, that rotational speed times 0 is just 0, right? But look, the further out you go, the faster these kids are moving, right? Just omega times r. And then acceleration follows suit right there, okay? You guys got that? rotational kinematic formulas. Ooh, these look a lot like the linear kinematic formulas. Like, for example, x equals v naught t plus half at squared. So now it's theta equals omega naught t plus half alpha t squared. So just turntable kinematics, right? We still got 5 variables we're juggling. In this case, time, angular acceleration, angular displacement, and then initial and final angular velocity. If you can identify any 3, you can get the other 2. Look at the units here. Units. Here's what is radians per second multiplied by seconds. What is that? Radians. What is radians per second squared multiplied by seconds squared? Radians. Ah, guys, radians plus radians equals radians. Look at that. And that's a common theme for every single equation that you guys have had in this class, has units attached to it. You can only add or subtract like units, right? Now you can multiply or divide different units, that's okay. But if you're adding and subtracting, they have to be the same unit. Right? If I say, like, what is 3 miles plus 5 seconds? That's a completely nonsensical question, right? So same idea for these other guys. All right, here's rotational kinematic formulas without the training wheels on them. Say without the units. I gave you guys some turntables. Said, hey, look, I got displacement versus time, velocity versus time, acceleration versus time, except the angular versions. So turntable physics, right? What if you have a turntable like rotating at a constant angular velocity or slowing to a stop? Like, what would those look like? We've done different versions of those. This slide right here is one of those scenarios, slows to a stop. So there's what angular displacement, angular velocity, angular acceleration as a function of time look like, right, for slowing to a stop, right? So they give this thing a counterclockwise spin, right? There's omega. And let's say there's a little bit of friction, a little bit of frictional torque. Oh, okay, that's why angular acceleration is opposite of that, right? This looks analogous to, say, like a car in a straight line or braking to a stop, right? X versus t, v versus t, a versus t. Those are the same type, same shaped graphs, right? Oh, yeah. Okay. I got some fun trivia slides. So old records from the 1960s, more recent CDs, 1990s, have actually different rotational type motion, right? Constant omega variable v versus variable omega constant v. A little bit of fun trivia there. Foucault pendulum. If you get swinging back and forth, the Earth rotates underneath it. A lot of the science museums, some universities have these. If you guys go to USF or UCF, look for this on campus, because I've seen it myself. Each of those has one of these fun buildings. Hey, here comes right. Guys, could you in this room, like inside these closed walls with the ceiling, we can't see the sky, we can't see the stars, we can't. Is there any way to prove that we're on a rotating surface in this room, that the Earth is actually rotating? Hey, that right there, that's what that's for. That's one thing it could show, right? Really subtle effect, the fact that the Earth is rotating, but that right there, right? Coriolis effect. So here's a similar type idea. Everywhere on the surface of Earth has the exact same angular velocity omega. We're all doing one rotation every 24 hours. That's a version of omega, right? The Earth is rotating at the same rate. But depending on your latitude, you could have a wildly different linear velocity. Let's call the North Pole like 0 miles an hour relative to its own axis. Well, the equator is pretty close to 1,000 miles an hour. Woo, right? Okay, so then if you change latitude, well, now there's a mismatch, right? You're coming from a latitude with one use for velocity to a latitude different use for velocity. If you get a pretty significant latitude change, you're going to notice that. If you have a low pressure system, a bunch of air wants to fill that void, that'll set up a hurricane because of this effect. Hurricanes in the northern hemisphere always rotate counterclockwise. Look for that next hurricane when you're off from school. Like, oh yeah, right, that's fine. Centripetal force lab. All right, big old table. You guys remember the slab with PVC pipe, string, Play-Doh canisters? I reference this slab all the time, right? There's 4 variables we're juggling. There's 4 variables. Right? I got some hanging weight, which is providing the tension in the string. So that's like a variable, right? We got the swinging mass. We got some radial size. And we got some speed to maintain a constant radial size. So, okay, so we have 4 variables. I split you guys up into 3 different experimental groups. You had two of those 4 variables were controls. One you're treating as independent variable, and then everyone was treating speed basically as a dependent variable, right? So what was the outcome? You guys drew all 7 of these graphs. Let's go through all these graphs. So some of you guys were changing out the swinging mass. Guys, for heavier swinging masses, how do you have to spin it? Faster or slower? Yes, slower for heavier masses. Or how about the other way? What if it was heavy and now you replace it with something really light? Well, okay, in that case, you have to spin faster. So some kind of inverse relationship between V and M swing. That's this top right graph right here. Inverse relationship, right? How do you figure out the equation of that graph. Well, that's really tricky to do. But you know a method from this class, which is linearization. How can we linearize? Okay, so I have to take some reciprocal. Let's say reciprocal of the mass. Right. Oh, okay, let's get a little closer, but it still looks kind of like a square root. So what if I square the v? Then it lines up in a straight line. These three yellow graphs on the right are all telling the same story, just a little bit different manipulation. Right? And the advantage of linearization is that you can very quickly whip off a slope, right? Rise over run, and then make an equation, linear equation. So in this case, it's kind of like y equals mx. Right? So v squared equals the slope of this line times 1 over the mass. Boom. Right. So now we know we've pinned down one of the relationships. How about the other relationships? What if you were changing out the hanging weight? Hanging weight is in true static equilibrium because weight down matches the tension up. Right? It's not moved. So guys, heavier weights. You have to spin it how? Faster or slower? Faster for heavier weights. Right. Now that was not a direct relationship. It does kind of curve down. So if you square the v, now that's a direct relationship between v squared and the hanging weight. Right. Now that hanging weight, again, equal to the tension, you could say that's like what's providing the centripetal force. Ooh. Right. One more. What if you change out the radial size? Or actually, let's think of this sort of backwards. Right. What if you spin it faster? Because if you spin it faster, what happens to the radial size? It gets bigger, right? You spin it faster, the radial size gets bigger, right? So some guys were trying, hey, how fast do I have to spin it for like 10 centimeters? And then 20 centimeters radius, and then 30 centimeters radius, right? And then you try different incremental radius, right? You got a graph that was, okay, it was also square root between v and r, square the v, that lines up, v squared versus r. Okay, so now we're gonna take these bottom three graphs, which we can definitely make equations for, because, right, okay. Right, and then, oh, look, everything's related to v squared. I put it all together, you get, that guy right there. Centripetal force is mv squared on r, where that m refers to the swinging mass. Okay, got it. Just like that. Right. So now you know the force that's involved for changing directions. Right? If you want to stay on a curved path, it could be constant speed, but you're still changing your velocity because your direction is changing. Right? And that's what that's about. Right? Now, if you divide by the swinging mass, it gives you centripetal acceleration, just v squared over r. And a good example of that is, let's say you and your friends are all in a car and you're exiting the interstate. So you're on a curved off ramp. So you're going just a little bit too fast. You're going pretty fast on a curved off ramp. You feel some G's building up, feel some G's, right? Oh, hey, that's a type of this right here. Speed of the car squared divided by raised curvature of the road. You get that, right? Yeah, since I'm making this video for all my classes, my AP kids, I tell them on the AP equations, AP gives them centripetal acceleration, v squared over r. It doesn't actually specifically print centripetal force. I don't know why. Anyway, so you guys go with centripetal force, right? That's a pretty commonly referenced lab right there. Right? Ooh, here's the turntable version of this, or anything that's like a solid disk that's rotating. Right? It's the same idea, centripetal force, centripetal acceleration, except now I have it in terms of angular velocity, which can be convenient for a number of reasons. Right? Guys, if we go back, let's go back to those kids on the merry-go-round. Where's those kids on the merry-go-round? Come on, kids. There's my 3 kids on the merry-go-round. Okay? You guys see this center expression right here? Linear speed is equal to angular speed times radial size, right? Could I just divide the, no, sorry, let's leave it like that, right? I could take this and I could substitute it for v. Omega times r is equal to v, right? Right. Let's go forward. Thank you. Right. What if I substitute it in for that v right there is equal to omega times r, right? That's all getting squared. One of the r's cancels, and then you get, bing, this right here, and then divide by mass, and you get the centripetal acceleration version, right? So let's think about mechanics of this. O'Neill cylinder is a really good example of application of this, right? So you're out in deep space, any kind of gravitational field is negligible. Earth is way off in the distance here, right? And all these people would be floating around like astronauts. But if you give this thing a spin, then now there's a normal force from the wall that's pulling them into a circle that's acting as the centripetal force. Right? Okay. Now, all these people might have different masses, but I bet they all feel the same artificial gravity, right? Right. In fact, if they're blindfolded and this thing's pretty big, they might think it's actual gravity. It might be really hard to distinguish the difference. Right? Right. What if you wanted to target 9.8 meters per second squared, make them feel at home? Right? Then let's say if I know the radial size of this thing, say so many meters, and I'm targeting 9.8 meters per second squared, I can calculate how fast I have to spin this thing. That's what omega is, right? Just do a little algebra, right? And the answer would be in radians per second, naturally, right? What else about this thing? How about How about this guy climbs this ladder? You guys see this guy climb this ladder? Gets to the central. Oh, you guys see this central dash line axis? This whole thing spinning about, right? What does he feel like right at the center of that ladder? Zero gravity field, right? Well, I guess zero artificial gravity. He feels weightless, just like a regular astronaut. If this thing takes like 2 minutes to rotate around, then yeah, maybe spinning real slow, but yeah. And the equation backs that up because this entire ladder and everybody has all the same omega, all the same turns per time, but okay, squared times 0 meters from the center is 0 artificial gravity. Ooh, yeah, right. Guys, if he was at the center of the ladder and he pushed off, is he just gonna float off into space? Yep, it's gonna float off into space. Spaceman. Turntable friction. Here for context, honors classes, we did this lab. My AP classes, I'm gonna save this for a review lab in the spring. So here's how this goes. We're gonna put either a coin or a mass slug on a turntable, and then give this turntable a rotation, and the coin will stay on there. Guys, what force is holding that coin on the turntable surface? Friction. Friction. Now, there's 3 forces. Got the weight, the normal force, but it's the friction force that's acting as the centripetal force. And that's the setup here. Friction forces equals centripetal force, right? All right, now spin a little faster, spin a little faster, spin a little faster. At some point, it's going to break friction and slide off. And at that point, if you can capture how fast this turntable spins at that moment, then you can calculate the coefficient of static friction between that coin and that surface. I do that, right? Well, I remember friction has something to do with coefficient of friction times normal force. Now, if we're talking about static friction, I have an inequality, because remember, it can like build up bigger, 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 up to that breaking point. I want to use the angular speed version of centripetal force. So m omega squared times r, right? So multiplying by radial distance from the center, right? Put it all together. The mass of the coin cancels, and here's a static coefficient of static friction. Okay? Now, if this omega angular velocity happens to be the angular speed that this coin broke friction and slides off, I can change this inequality to equality. I can just say equals, and you can solve for it. Okay. So honors classes did that lab. Okay, there's the lab table, goes along with that. Right? If you're keeping track, at this point, there's actually 3 different kind of accelerations that we're juggling. Keep track. So let's start with the green one, because that's the first one you guys learned. Linear acceleration, or tangential acceleration, if you like. Sometimes it's called for context of a turntable. Right. Now it's a change of velocity per change in time. Now the turntable does have to be changing how it's rotating for you to have this at all. It has to either be speeding up or slowing down, rotating. If it's a constant angular velocity, then this green one's equal to 0, right? Because another perspective is angular acceleration times radius, and you guys saw that one with the 3 kids on the merry-go-round. The flip side of the green one is the red one. Alpha is angular acceleration, so this is like speeding up spinning or slowing down spinning. So it's change in angular velocity per time interval, right? And it connects to the green one by saying that tangential acceleration divided by radial size, right? And all points on this turntable would have the exact same alpha, the same angular acceleration, right? Regardless of what they're pretty close to the center or pretty close to the outside, doesn't matter. They have all the same alpha, right? How about centripetal acceleration? This gold one on the left side. Okay, so that is a like center-seeking acceleration. Can be the other way, right? I should have another formula up here that says centripetal force divided by mass, because that's the same thing. So centripetal force is always a center-seeking force. So that vector right there. You could also calculate it by doing linear speed squared divided by r, or angular speed squared times r. Okay, you guys good with 3 kinds of acceleration?
Yeah.
Right. All right. Next, conical pendulum. You guys see this big red mass right here? Guys, how many forces are on that big red mass? 2. I see a weight acting straight down, and the tension in the string pulling up to the left. That's it. 2 forces, right? Now those forces are, well, not completely balanced. Oh, maybe they're balanced vertically, right? Do you guys think if you, guys, which force is bigger? Has bigger magnitude? The tension. Tension is a bigger force, and you know it's a bigger force because you can break it into components, and the vertical component, I'll call it F tension times cosine theta, has to match the weight. Therefore, hypotenuse of this triangle would be the longest side. So yeah, tension is greater than the weight. Right. So that's what this top line says right here. tension force times cosine theta has to balance with the weight. Look at their series. Now, horizontally, different story. Horizontally, there is a net force. You can see it's tension times sine theta. And of course, the theta we're playing off is relative to the vertical. Right. So Ft sine theta is the net force, which is acting as the centripetal force, which is holding this mass on this curved path. There you go, right? Ooh, when you guys did a lab version of this, maybe this angle was like 85 degrees. We were assuming you guys' string was approximately horizontal. Can the string ever be perfectly horizontal? No, because the swing mass also has some weight. But for your labs, like, okay, it's close enough for your lab, right? Guys, would this mass right here be in true static equilibrium on this curved path of constant radial size? No, because anything on a curved path has to have a net force, mv squared on r, right? No, guys, if you take some science and engineering classes in college, you might hear the phrase dynamic equilibrium, which this would be an example of. And the idea there is being that you swing at such a speed that this radial size doesn't change, right? So you could call it dynamic equilibrium, but it's not true static equilibrium, right? Because there's a net force. Hey, vertical loop free body diagram. Do you guys remember I had some water in a cup on the string? And I whirled that around in a vertical circle. Yeah. Right. And now if you do it plenty fast enough, like the water stay in the cup, no problem, right? But what if I slow down a little bit? Slow down, slow down, slow down. At some point, the water's going to fall out of the cup. Or how about this? Here's another story that attaches to this. Do you guys remember a roller coaster? What if you send a roller coaster through a vertical loop? Right? Or you guys saw a bowling ball, is the same idea, right? Go around vertical loop, right? There's still minimum speed to get around the top. What is that minimum speed? Right? Let's look at these free body diagrams. So you got weight down, the tension pulling towards the center, definitely an unbalanced force at the bottom, and then the top. Notice it's the same weight. It's the same weight everywhere, right? But the tension is probably changing, right? Yeah, tension is going to be changing, right? And the tension could get smaller, smaller, smaller. The tension could go to zero. Suppose, let's go back to my water in the cup example. Now I've got a goldfish swimming in the water. You guys see the goldfish swimming in the water in the cup, right? If it just barely gets around, I bet that goldfish is getting pretty nervous. Feels pretty weightless, kind of like an astronaut for just for one instant at the very top there, right? We're gonna say the sum of the forces is acting as the centripetal force holding on the curved line path. That's the weight plus the tension. But I'm gonna let that tension go to zero for like the so I can calculate the minimum speed to get around. Then it ends up being, here's the answer, square root gr. I got a question earlier today. What is that in terms of angular velocity? Oh, you could do that too. I can substitute v is equal to omega times r. It's squared. One of the r's divides. Right, divide that over. So omega minimum would be the square root of g divided by r. Ooh, that's what that would be. Car turns on a big track. Suppose one day you're a traffic engineer, and let's say you're working in a state that actually has ice in it. That's not Florida. And the road's getting iced over. You want to design an off ramp from an interstate. A bunch of cars zipping off the interstate, going pretty fast. They got to make a turn, but the road's iced over, so they don't get the advantage of friction. Can you make a turn on a road without friction? Yeah, you can bank it. Guys, this car right here has how many forces on it? 2. Weight down, normal force up to left. Hey, does that look the same as sort of like the conical pendulum? It does, except instead of tension and strain, now it's normal force provided by the road. It's a really similar idea, isn't it? Right? I'm going to break that. Oh, guys, if you're inside that car, guys, everybody look up here. Look up here. If you're inside that car making that big turn, so you're going pretty fast, pretty tight curve, do you feel a little bit heavy? A little bit heavy, right? Yeah, feel some G's, right? That might be a hint that this normal force is greater than the weight of the car, right? Which it is. Break that normal force into components. Notice we're using a Cartesian system that actually is aligned to gravity, not the surface of the road, but to gravity, right, guys? The vertical component has to match the weight. So normal force times cosine theta, and that theta is that theta, right? Normal force cosine theta is balanced with the weight. Normal force sine theta is the net force, which is mv squared on r. Centripetal force. Put it all together, this leg compared to this leg, there's a tangent relationship. Right. If you want to figure out how much you have to bank the road, you know the speed limit of the car. Notice mass of the car cancels out. Right, mass of the car cancels out. Here's speed of the car. Here's gravity field of the planet. Here's radius curvature of that turn. Take the inverse tangent of that ratio. That'll tell you exactly how to bank the road. Okay, right? Great. Now you guys can be traffic engineers. Kepler's laws of planetary motion. Kepler, looking at a bunch of planetary data, very precise astronomical data. Where exactly is Mars night by night? Where is Jupiter night by night? Where's Saturn night by night? Right? They can see those planets, right? And came up with planets actually follow elliptical orbits, not exactly circles, although they're kind of circular-ish. Sometimes we estimate it like that. But a circle is kind of a tenuous orbit because an asteroid slams into you. Well, now you're just going to spiral into the sun. But ellipses are a bit more stable. Got second law, equal areas, equal times. Now, third law, I found this proportionality between the time period to go around the sun and the average distance, right? So time period squared, proportional average distance cubed for all these different planets. Now, if you bring in, guys, everybody look up here, everybody's learning. I'm giving you guys all the answers to how the universe works. If you bring in Newtonian mechanics, universal gravity, and come out as centripetal force, you can get an exact equation out of that. And here's the exact equation, kind of an updated version of Kepler's third law. So since we're getting to universal gravitation, you guys know you're about to see an inverse square law with universal gravitation. So let's talk about inverse square law. Here's an example with light. You guys ever want to look at the sun? You guys ever look at the sun? Don't look at the sun. It'll burn out your retinas. Be the last thing you see. Can you look at the stars at night? Stars? Yeah, you can look at the stars. Hey, aren't those just suns? Oh, but they're really far away. So light intensity tapers off 1 over the distance squared. You can see that here. That's the fact that we live in 3 spatial dimensions, right? That's a consequence of that. Guess what works the same way? Hey, gravitation also tapers off 1 over the distance squared. So how about between Earth and the moon? There's the Earth, there's the moon. Guys, look up here. Got a question for you guys. Here's the moon pulling on Earth. Here's Earth pulling on the moon. Are those forces identical? Yep. That's Newton's third law all over again. I should say my picture is not to scale, kind of cartoony version. Here, I'll tell you guys what would be to scale. If Earth was the size of a basketball, then the moon would be the size of a tennis ball, and they would be 24 feet away from each other, which is most of the width of this room. So the Earth could be a basketball over there, the moon could be a tennis ball over there. Right. So what we got? What's the gravitational force? Got universal gravitational constant, which is this tiny, tiny, tiny number. Mass of the Earth, mass of the moon, distance squared. That's a center to center distance, right? You guys see all that? Inverse square law. Von Jolly figured out what is the universal gravity constant way back in 1880. He has this tenuous balance. He has 6 tons of lead, restoring force, boom, divide, gravity, universal gravitational constant is that tiny number. Orbital speed. How fast do you have to get a satellite going to orbit the Earth? Let's say you want to solve for a circular orbit, like the minimum speed, circular orbit, right? Now, my AP students, since I'm using this recording for all my classes, my AP students have to know this because this would be a completely fair AP question. You say, well, centripetal force, mv squared over r, is provided by universal gravitation, gmm on r squared. There's only one force, gravitational force on, say, like a satellite, right? The mass of the satellite cancels out, and the necessary orbital speed is square root gm on r, just like that. Now, again, that's for a circular orbit. Ideally, maybe speed it up a little bit, give it like an elliptical type orbit. Say keep speeding up, speed up, speed up, speed up. Eventually you approach, this right here, escape speed will just like fly off away from the planet forever, right? That comes from conservation of energy. Actually, I'm not going to expect any of my classes to know that. And even my AP students, that's not going to show up on their exam either. Right? But let's say it all together. Right, so here's Earth. Here's this guy standing on Alaska. He experiences this here gravity field. Universal gravity constant, mass of Earth divided by raised to the first squared. Here's the orbital speed of this green satellite. Here's the escape speed of this red rocket. I should say, too, you don't actually have to reach escape speed to escape the gravity of a planet, as long as the engines are burning. If the engines are, you can escape real slow. That's okay. Right? But if you cut off the engines and you still want to escape the gravity of the planet, you do have to go at least that red speed right there. Eggshell planet. All right, so exploring the galaxy. Hey, there's a planet. We're marching around on this planet. Something weird about this. Start digging a tunnel. Oh boy, this whole thing's hollow. We're on a giant eggshell. If you jump inside that planet, which you're perfectly okay walking around, you can walk around on the surface. It'll pull you down towards the center. Right? If you jump inside, now you're floating around like an astronaut. It's gravity-free interior. There's a single point where the gravity field cancels out. And that might seem kind of abstract idea. Okay, what is that good for? There's probably no hollow planets, right? But you can use this to calculate something for a solid planet. Because if you're in a solid planet, let's say you tunnel down towards the center of the planet, right? Like, how's the gravity field change? Well, if you go through into a really deep tunnel, everything above you in elevation is essentially a series of eggshells that all cancels out. So if you tunnel down, it's as if you're standing on a smaller planet beneath you in elevation, right? So let's do that. Let's do journey to the center of the Earth. Let's ignore all the molten magma down there, right? So on the let's make a graph while we're at it. Let's keep track. Let's do gravity field as a function of distance from the center, right? Right. You guys see that, right? On the surface, we got 9.8 meters per second squared. Bam, there's a point on the graph. Let's say we tunnel down to the center. There's hey, I found a cave in the center of the Earth. I'm just making believe, right? Guys, what's the gravity field at the center? 0. That was a Kahoot question yesterday, wasn't it? Right? You can show that there's a linear relationship. So if you're like halfway down, like this guy, you experience half his weight from the top. Suppose he weighs 100 pounds at the surface, 0 pounds right at the center of Earth, and probably about 50 pounds right here. Okay. How about this? Let's climb a tower that is equal, that has the height of the radius of the Earth, right? Right. If he weighs 100 pounds at the surface of Earth, what does he weigh at the top of this tower? Where he's doubled his distance from the center of the Earth? 25 pounds, right? He has a quarter of his weight. Why a quarter of his weight? Inverse square relationship. And he also experiences a quarter of the gravity field, right? Let's say you take off in a rocket, you just get further from Earth. Now the gravity field from Earth is going to asymptotically approach 0. So it looks like this right here, inverse square relationship. Okay, put it all together. You guys go with that graph? Okay. Tides. Okay, so this comes from the fact that Earth has a diameter, right? No, the main driver of the tides is the moon. There's some other effects too. The sun has a small effect, right? But the main driver is the moon. So there's a close side and a far side of the Earth to the moon, right? The close side is a little bit stronger gravity. The middle is like Goldilocks. The far side is like the weak side, right? That's why we get 2 tides every day, or 2 tides, right? The moon has a similar type of effect going on. The moon is tidally locked to Earth. That's why only one side of the moon ever faces Earth. Before 1957, we had no idea what the opposite side of the moon looked like, the far side of the moon. So we never sent anything in space before 1957. Right? Lagrange points. Here's another fun trivia. So points of gravitational stability. I think James Webb's Space Telescope, I want to say it was launched 2 years ago, I think it was. I think, right? Is actually orbiting this L2 point. It's kind of easy to keep it right there. Right? All right, that's going to bring us to energy and momentum. I put a bunch of units on this slide. Energy measured in joules, power measured in watts. That's energy per time. And then when we eventually get to momentum, that's something to do with mass times velocity. It's kilogram meter per second. Transfer of momentum is called impulse, change of momentum, measured in Newton seconds. Guys, kilogram meter per second and Newton seconds, are those identical units? Are those identical? Yep, same thing. Right. Right, so let's get a closer look here. Energy measured in joules. 1 joule breaks down into Newtons times meters, which further breaks down to kilogram meter squared per second squared. Right. Now, pause here. That might look a lot like torque, but remember, that's a completely different concept. Torque actually do list it in Newton meters, but energy we're going to call joules. That's 2 totally different concepts. Okay? Power measured in watts, which is a rate of work, rate of energy transfer. I'll call that joules per second, right? Which further breaks down into those base SI units. Right? Oh, like a light bulb might have like 40 watts. 40 joules per second. Right? Here's forms of mechanical energy, which are the forms that you care about for this class. Now, this is not all the forms of energy. I don't have thermal energy up there, although we'll do a little bit of thermal energy next semester. I don't have chemical energy, energy stored in AA battery, energy stored in gasoline, energy in food calories. None of that's there, right? But I have these forms of mechanical energy to care about for this class. Now, energy is conserved in the universe. Let me go back a slide. The number of joules in the universe is the same. It's conserved. The sort of bending of that rule is you can make a case for like nuclear energy. But aside from that, right? If you do energy accounting, you can solve a number of problems that way. Right, so what have you got for mechanical energy? Well, work, energy transfer, let's see, if you push something with a force for some distance, now that's a dot product, so you're only multiplying the parallel components. You transfer some energy that way, right? Hey, suppose you lift something for some height. Say I need to lift something with a force equal to its weight. For some height could be this way. Hey, that's mgh. So the work you do lifting something is equal to the potential energy you give it when you set it on the shelf. Hey, that was also a recent Kahoot question. Right. Now, there is a more universal form of potential energy. That's this green one. That's if you have a changing gravity field. Don't worry about that so much. It's just that maybe like once or twice ever in this class. I'm not gonna test you guys on that though, right? You use that in escape speed you might need, right? But even if you go from the top of Mount Everest down to sea level, that gravity field barely changes, right? So you just care about MGH for potential energy, right? How about energy stored in a spring? Could be 1/2 kx squared. Ooh, I also remember a different formula called Hooke's law was F equals kx. Now that was forces, but the work you need to stretch or compress a spring, you might say force times distance, but it's a variable force, right? So you can play off the spring constant. How stiff is a spring, right? So that's 1/2 kx squared. So there's your energy stored in a spring, right? Energy of motion, 1/2 mv squared. So something has a mass and a speed, has some kinetic energy, right? Now this rotational kinetic actually did come back more recently with like a ball rolling downhill. So there's energy involved in rotating. So 1/2 I omega squared. I, you guys know, is rotational inertia, right? And then omega is angular velocity, put it all together, right? So like a ball rolling downhill, I could say at the top of the hill, it's all mgh. And at the bottom of the hill, well, now it's a mix of energy. It has both linear kinetic energy, translational kinetic energy, but also rotational kinetic energy. So you have two types. You have to add them up. And that V and that omega would be related to each other, right? Because you could say omega is equal to V divided by R, and you could solve for things like linear speed at the bottom. Right? That was something you guys did recently. You guys remember a ball rolls down incline? What's the speed at the bottom? Right? All right. Well, that is as far as I've been getting today. So that is our pause point. I think that's going to be the winner for the Google Classroom video. All right, you guys have a great afternoon, and bring your laptops tomorrow for more Kahoot.